In this video, we'll continue our discussion about invariance, and we'll actually be able to parse through a little bit of the anatomy of a topological space. In the next video, we'll go into a lot of hairy details about what topological spaces actually are, and how we can actually define the real mathematical object topological space. But for now, we'll have to rely mostly on our intuition, which is fine for what we're doing today. Our first little invariant is something called genus, and I mentioned it in our live session, but just to remind you, the genus of a surface is simply the number of holes it has. Now this is a little bit tricky to define, and it's best explained through a picture. So our surface can't just be any old surface. It has to be a surface that has no boundary, it has no edge. So in other words, I can't consider this object here, the cylinder, to be of genus 1 because it does have a boundary. It has a boundary like this. So when we're talking about genus, we're really talking about these surfaces like the torus, which are kind of smooth all over the place. And of course, the genus 1 surface is the torus, but we could very easily extend this to a genus G surface just by adding in more holes. And in general, to draw the genus G surface, you have to pretend like there's G holes and just create a little picture here that maybe is not incomplete here. So has some more holes. Okay. So that's generally how we draw surfaces of genus G. They come actually very important in the study of low-dimensional manifolds, which is something that we will get to by the end of this program. Now, just be cautious here. Only this one here is called the torus. Okay, this is not the 2 torus. It is not the 3 torus if it has 3 holes. We just say the surface of genus G. Actually, sometimes to be super specific, we will say the Riemann surface of genus G. Okay? And the word Riemann in there is just able to capture the fact that it doesn't have any boundary and it's like sort of smooth all over. Our next property is also quite intuitive. It's called connectedness. In particular, there's a difference between connectedness and something called path connectedness in topology. Path connectedness is very intuitive, and it is what you would sort of think when you were told connectedness. Connectedness, the word itself, on the other hand, means something different, and although the two often overlap, there are actually cases of topological spaces that are connected and not path connected. So when we're talking about connectedness, usually we will mean path connectedness, and I will show you here what path connectedness means. We won't be able to go into a full discussion about connectedness. It's a little bit above what we are trying to go for here. So a space is said to be path connected if every pair of points, and I'll call them x1, x2, on the space can be connected by a path. And I would just want to remind you that in our live session, we discussed what a path was. It's a continuous function from the unit interval to our topological space, and it just has to be continuous. So here, for example, is an example of a path. Right? Now, this surface here, it's actually a surface of genus 1, is actually a path-connected topological space. Now, here I demonstrated a path between these 2 points, x1, x2, but you can very easily envision for any 2 points that I pick on this, I will be able to draw a path. Same thing here goes for this annulus. Now, when we're looking at this, I want you to think of it as a bit of a ring, right? So here we have an annulus, and it too is path connected. As you can see, any point can be sort of cycled around to any other point. We can just go around this hole. It's not a major obstruction. However, if I were to do something like remove this hole, so let me actually do that here. I'm going to make a dotted line here, then I'm going to make the hole again, and continue the dotted line, and then just do this right here. Now, what do I mean by this dotted line? Well, by this dotted line, I mean that I've made a bit of an incision into my ring, And so this is no longer path connected, because if I pick any point here, there's no way to bridge the gap over to another point here. Although, notice that locally, if I just take a little section of my ring, it is path connected, right? These 2 points here are in this little disk. They're nice and happy. They are path connected. However, these 2 green points on the global scale, they are not. There's no way to go around here and pass any of these barriers. I can't sort of cheat my way around this gap here, right? So it doesn't even have to be a very big gap, but as long as the gap is there, my space is not path connected. This illustrates that path connectedness is a global property. And what that means is that I can't just zoom into my topological space here to determine whether or not it's connected or not. I have to actually be able to look at the whole big picture. This is illustrated a little bit better in this next example here, where I've just taken the 2D plane and I've deleted this y-axis. Now this again is not path connected for the exact same reason. It's not path connected because if I take any 2 points here, I will be unable to bridge over this gap, right? There's no way I could go through it. Now, if I were to just allow one single point on the y-axis, the situation changes entirely, right? Because I can now make it path connected by drawing a path here and then drawing a path anywhere else. And of course, if I were to pick 2 points that were on the same side of the half plane, then there's no problem at all. Obviously, any 2 points can be joined by a path like so. Right? So this shows you really how critical path connected is. It can change completely with just the addition of 1 point, or the removal of 1 point for that matter. So while this space here was not path connected, the R2 where I remove the y-axis, now I have the same idea, except this is usually called the z-axis for the purposes of 3D space. Now we have the same idea where the vertical axis is removed, but now we have an extra dimension to work in. Notice now that our path is path connected, because for any 2 points that I pick here, let me just draw that a little bit better. And let's say I pick 1 point that's like right over here. Oops. Okay. Okay, hold on. There we go. That's what I wanted. Right. So for any of these 2 points here, it's actually easy for me to draw a path. I just have to be able to skirt around this this deleted green line here, right? Now, there's obviously multiple ways I could go about it. I could go around. I could like make a path that does something like this. All sorts of funky stuff. The point is that it actually poses no obstruction anymore now that we've added the extra dimension. Okay. So that's pretty cool. Yeah, so what I mean when I say this is a topological invariant is that if 2 spaces are said to be homeomorphic, then they must have the same type of connectedness. Connectedness is basically an on and off switch. You're either connected or you're not connected. But the fact remains that if your spaces are homeomorphic to each other, remember that means deformable to one another in a sort of nice, smooth way, then they are actually going to have the same type of connectedness. They're either going to be both disconnected or both connected. That's going to play a much more important role when we start talking about boundary, which is point number 4. But before we get there, we need to talk about dimension, which is point number 3. So the dimension of a topological space describes intuitively what kind of depth of structure is present in the space. In our example here, we had a 2-dimensional space. And notice that deleting 1 line already made it disconnected. It was no longer path connected. However, in this space here, which was a 3-dimensional space, right, the same thing, removing 1 single line, didn't actually change path connectedness. So really, dimension is a way of measuring how deep the structure of a space is. And it also, in a way, intuitively describes how much moving room you have. There are a lot of really interesting results about dimension. We'll cover a lot of them in our session. So topological spaces can have a boundary. They might also not have a boundary. But in any case, we will always assign the dimension of a topological space by its interior. We won't really pay much attention to the boundary. However, the dimension of the boundary itself is usually related to the dimension of the actual topological space. So instead of giving the rigid definition of dimension, which is actually quite complicated and involves a little bit more machinery than we have at the moment, I'll just give a couple of examples of topological spaces of various dimensions, and hopefully you'll get the idea. So things like curves and paths, the circle, and actually intervals as well, intervals on the real line, those all constitute one-dimensional spaces. Intuitively, they're one-dimensional because no matter what you do, if you stand on this one-dimensional space, there's only two ways you can go, up or backward, forward or backward, right? And as soon as I stick an arrow here, right, that already gives me an orientation. There's no other way I could somehow flip the arrow around without actually like turning back on myself. So this is intuitively what describes a one-dimensional space. On the other hand, two-dimensional spaces have a little bit more moving room. These include the cylinder, the sphere, the surface of the sphere, which is going to be called the two-sphere in a little bit, the torus, and RP2, which is an example that was presented in one of the exercises this past week. So if you haven't seen this and you're a little uncomfortable with this, you should go and check out those exercises, at least read through them, because they're not going to play a really critical role in our theory, but they are a useful class of examples to have. So make sure you know what this is. It's really interesting. So intuitively, a two-dimensional object is a surface, right? So it can be shaded in, and the point is that near any point on this two-dimensional surface, I can go in a variety of ways. In fact, the sort of variety of ways I can go is sort of described by a little mini two-dimensional coordinate system. Obviously, I can't extend this too far or else I'd be going off my topological space, but at least locally, this is the right idea. Actually, this particular construction here of assigning a mini coordinate axis to every point is exactly what describes dimension in the general case. So with that being said, you may be inclined to guess already what a three-dimensional object would generally look like. Well, it's just some sort of solid thing that has a little bit more moving room. Rigidly, it means that everywhere I go inside my space, so let's pick a point like in the middle of this sphere, and now I'm including the points inside the sphere. Usually when we include the points inside the sphere, we call it a ball, and it's going to be sort of thought of as a solid object. Now, what this means is that we can actually assign inside our little point a mini three-dimensional coordinate axis. Again, of course, we can't extend this to infinity like we usually do, or else we would go outside of our ball, but at least locally, it makes sense. Now, here are some other examples. These are actually much more complicated objects than their names suggest. Now, we've seen the word torus used to describe a surface like this. The 3 torus, again, is not just a torus with 3 holes in it, nor is it a solid torus, although a solid torus is an example of a three-dimensional topological space. The 3 torus and the 3 sphere are more complicated objects, which we will eventually get to in our discussion of topology. But for now, you'll just have to take my word that these 3's over here mean a little bit more than just what the dimension of that space actually is, and we will eventually get to them. So usually we will not consider spaces with components of different dimensions. So for example, a sphere surface with a loop attached to it, although they are still topological spaces if you define them correctly. But for what we're doing here in this program, this is not usually going to be an important consideration. Okay, now we come to a very critical definition, and this is a definition that will be used a lot in the next video. We are going to define the unit n-ball. Now, a unit n-ball is just the set of points that are distance less than 1 away from 0. Actually, I should put an equal sign here because it also includes the points that are distance 1 away from 0. In Rn, so here's R1, here's R2, and here's R3, right? This is going to look very different, but in general, it carries the same property, right? This is the description of a unit n-ball. In R1, it's just a closed interval from -1 to 1. In R2, it looks like a unit circle, but with every point inside included as well. And in R3, a unit 3-ball looks like the set of points that are exactly distance less than or equal to 1 away from the origin. Now, this is a solid ball. It's not the surface of a sphere. And I want you to notice, first and foremost, that Bn actually has to live in Rn, right? The unit 1 ball does not make sense in R3 because that would just contain this line over here. It clearly is not going to satisfy the definition of an n ball in a higher dimensional space. So we can actually only use this definition of the n ball in a space that has the dimension exactly n. If we ignore the boundary of our ball, we will often call it the open unit ball, or in general, when we're not just putting our ball centered at 0, we will call it an open ball. What this looks like graphically in R1 is removing the boundary. So we're removing the caps on our interval, the -1 and the 1. And so now we get an open interval. In R2, this would look like a disk, but without its boundary. And we'll usually do this with a dotted line. And in R3, well, this is a little bit more difficult to draw, but what I can do is I could just draw a dotted line over here, and you would have to sort of be able to see that dotted everywhere implies that it's not included. Okay, and that is called an open ball. It's going to be super important in the next video when we define something called a topology on Rn. And the last thing is an n-sphere. The n-sphere is one of the trickiest things to name because it is one of the things that is most commonly misinterpreted because of this convention with Bn lies in Rn. So people think that the n-sphere will of course lie in Rn, but that's actually not true. The n-sphere is the boundary of the n-ball, and it is the set of points that are exactly 1 away from 0, not in Rn, but in Rn minus 1. Okay, and this is a super important point. People will always mess this up. For example, actually it's an Rn plus 1. My bad. So people will always mess this up. So here's the thing: the set of points -1 and 1 in R1, that's the 0 sphere. We will write it as S0. And now it makes sense why back up here when I said the circle, I called it the 1 sphere, because what it is really is just the boundary of a 2 ball. It's just a circle, right? So it's this thing over here, right? This is my S1. And then the surface of a 3 ball is, well, it's a little hard to draw. I'll just outline it again. But you would have to understand that because I'm not shading in the inside, it's not solid. So this is just the surface. And this is called the 2 sphere. Now this is all incredibly confusing. Why is S2 in 3 dimensions? Why is S1 in 2 dimensions? It's just the convention. This is actually a really important way of defining the n-sphere, because it means that in order to find the dimension of Sn, we just have to look at the n in particular. So although S1 does live in 2 dimensions, it is still a 1-dimensional topological space. Although S2 lives in 2 dimensions, it is still, in 3 dimensions, it is still a 2-dimensional topological space. Our last invariant is called boundary. So if 2 topological spaces are homeomorphic, then their boundaries have to be homeomorphic as well. Notice we haven't said that a topological space must have a boundary. For example, the torus, right? It's nice and smooth. It's a 2-dimensional object that does not have a boundary. If it did have a boundary, there would be a sort of edge that you could fall off over, but we know very well that it's nice and smooth everywhere, right? So there's no rigid edge for my torus. Okay, so what this means by their boundaries have to be homeomorphic as well is exactly what we described in the previous 3 types of invariance, which means that if my 2 spaces are going to be homeomorphic, well, their boundaries better be similar as well. This immediately tells us that things like the solid torus and the solid surface, the solid genus G surface. So by solid, I really mean like it's been filled in. This is just bad terminology here. But these 2 cannot possibly be homeomorphic because their boundaries are respectively the torus and the surface of genus G. right? In here, I've drawn the 2, right? And just notation, by the way, usually when describing the boundary of X, we will write this little curly d X, right? Now this thing here is commonly referred to as a partial. I've also seen people call it del, but I prefer not to use this terminology. I'll usually say partial, or I'll say boundary, to be like very explicit. Okay? There is a reason why this particular symbol is chosen, but that's far beyond the scope of what we're trying to do in this program. So the last few examples are nice and fun. We're going to show that every single one of these steps in the construction of the torus are not homeomorphic to each other. So in particular, none of the steps that we described can be considered homeomorphisms, even though you can imagine like doing them physically in real life and whatever. So this here is not a homeomorphism because look at its boundary. This is a square. Its boundary is actually just like that. It's just a square, right? Whereas on the other hand, the boundary of the cylinder is consisting of 2 components, right? So if I were to isolate it, it would look like this, right? 2 components, right? Now this here is path connected, and these 2 circles here are clearly not path connected. So this cannot possibly be a homeomorphism, but by what I said above, the boundaries have to be homeomorphic to each other if they are to be a homeomorphism between the actual spaces. Now, perhaps now you can see why the cylinder and the torus are not homeomorphic. It's for the exact same region. The boundary of the torus is empty, right? There is no boundary. Whereas on the cylinder, there are exactly 2 boundary components. Therefore, they cannot actually be the same. And finally, right? So here I have a very special example. This is an exercise in dimensionality. Okay, so what I've drawn here is actually something very strange. This is a knotted surface. It is a surface that is intersecting itself. Okay, and back here it continues, right? And it actually goes up through here, passes up here, and it continues back down here. Okay. So this is a bit of a complicated object here, but this is a surface, and so is my 2-sphere. Okay. By the way, RP2 is a kind of surface similar to this. It's sort of like knotted with itself. It doesn't really nicely embed into 3-dimensional space. But that still doesn't mean it's not a topological manifold. We can analyze its boundary. Okay. So here we have 2 examples where the boundary is not homeomorphic to each other. So here we have a boundary that is completely empty. So I'll write here, the boundary of S2 is empty. And you can see this because there's no way you could fall off the sphere if you were just walking all over it. Whereas this one here, it clearly does have a boundary. It's this white curve that I've drawn here. And maybe what you would like to think about now is how this white curve can be described completely in isolation of the knotted surface that I've described it on. So in other words, think about this, right? And maybe as a fun exercise, show or think rather why this is not easily deformable to S1, okay, the unit circle. Now notice here I didn't say homeomorphic. This is partly because there is a little bit of a quirk with the word homeomorphism that allows you to turn this knot here. This is actually a knot, you can't undo it. It allows you to turn this knot into S1. That's a very peculiar thing that has to do with the intrinsic definition of a homeomorphism, and we may touch on it, but for now, just think about why using like an elastic band or something, this could never be easily deformed into the circle without passing through some strings through itself. Okay, and I think that's where I'll stop it for today.